Tonight, we're going to cross the distance to the nearest star beyond our solar system, a distance that sounds almost surprisingly small. Proxima Centauri is only 4.24 light-years away. On a map of the Milky Way, it is practically next door. But those 4 light-years contain roughly 40 trillion kilometers of almost completely empty space. Voyager 1, moving at about 17 kilometers per second, would need around 75,000 years to cross a distance like that. Even if we could somehow send the fastest spacecraft humanity has ever built toward Proxima Centauri at its record speed and keep it there, the journey would still last thousands of years. And the faster we try to cross that gap, the stranger the problem becomes. Tiny grains of interstellar dust become dangerous projectiles. Stopping at the other end can require almost as much energy as getting there. A message sent home after arrival would still need more than 4 years just to reach Earth. So tonight, we're going to find out what 4.24 light-years actually means, why the empty space between neighboring stars is so enormous, and why reaching even the closest star may be far more difficult than the number itself suggests. Before we continue, if you enjoy exploring the strange realities of space with us, you can take a second to like the video or subscribe. It helps this channel reach more curious minds like yours. The first thing to understand is that Proxima Centauri really is close by astronomical standards. There is no hidden star sitting halfway between us and Proxima, waiting to make the journey easier. As far as known stars are concerned, this is the shortest interstellar crossing available to us. Proxima belongs to the Alpha Centauri system, along with Alpha Centauri A and Alpha Centauri B. Those other 2 stars are slightly farther from Earth, at roughly 4.37 light-years away. Proxima sits a little closer, which is where its name comes from. The word Proxima comes from Latin and refers to something nearest or closest. That makes it an unusually useful destination for understanding interstellar distance. We are not choosing a particularly remote corner of the galaxy. We are choosing the nearest star nature has given us. And yet its distance works out to around 40 trillion kilometers. That figure is so large that ordinary comparisons begin to lose their usefulness. Driving the distance of Earth's equator once is about 40,000 kilometers. Crossing the gap to Proxima would require repeating a distance of that scale roughly 1 billion times. Even that comparison is difficult to hold in your head because 1 billion repetitions of anything quickly becomes abstract. Astronomers therefore use another unit for distances within planetary systems called the astronomical unit. 1 astronomical unit is approximately the average distance between Earth and our star, about 150 million kilometers. Proxima Centauri is roughly 268,000 astronomical units away. That number gives us our first hint that this is a different kind of journey. Neptune orbits at roughly 30 astronomical units. Pluto averages around 40. Voyager 1, after traveling continuously since 1977, is only a little over 160 astronomical units from our star in 2026. Proxima is still thousands of times farther away. Even the record speed of Parker Solar Probe does surprisingly little to change the picture. During its closest passes, Parker has reached roughly 690,000 kilometers per hour. Nothing humans have built has ever moved faster. If a spacecraft could somehow travel directly toward Proxima at approximately that speed without slowing down, which Parker itself cannot do, the crossing would still require around 6,600 years. That is not a realistic Parker Solar Probe mission. Parker reaches its tremendous velocity by diving extremely close to our star and converting gravitational energy into speed along its orbit. The comparison simply gives us a useful ruler. Take the fastest motion we have ever produced with a spacecraft, preserve it impossibly well for thousands of years, point it toward the nearest star, and the destination remains thousands of years away. Voyager gives us the opposite kind of ruler. It is much slower, but its motion resembles an actual spacecraft coasting outward into interstellar space. At around 17 kilometers per second, covering 40 trillion kilometers, would require something on the order of 75,000 years. 75,000 years ago, our own species was living in the late Stone Age. Agriculture was still tens of thousands of years in the future. There were no cities, no written languages, and no spacecraft waiting to begin journeys between stars. And this is the distance to the first one. The problem is therefore not that Alpha Centauri lies on the opposite side of the Milky Way. The galaxy stretches for roughly 100,000 light-years. Proxima is barely more than 4. The unsettling part is that 4 light-years is already enough to overwhelm nearly every form of transportation humanity has developed. To understand why, we need to stop looking at the full 40 trillion kilometer gap all at once. Instead, we can begin at Earth and move outward, one familiar boundary at a time, past the Moon, the planets, Pluto, Voyager, and eventually the outermost reaches of our solar system. Only then does the real size of the space between stars begin to appear. A useful first marker is much closer than any planet. The Moon orbits Earth at an average distance of about 384,000 kilometers. Apollo astronauts crossed most of that gap in roughly 3 days. Even today, the Moon remains the farthest place human beings have physically traveled. Move outward from there, and the scale changes quickly. Earth travels around our star at an average distance of about 150 million kilometers. Astronomers call that distance 1 astronomical unit. It provides a convenient ruler for describing the solar system because most of the planets can be placed along it, using numbers that remain reasonably small. Mars follows a more elongated orbit than Earth, so the distance between the two planets changes dramatically. At favorable times, Mars can come within roughly 55 million kilometers of Earth. When the planets are positioned on opposite sides of their orbits, the separation can grow to hundreds of millions of kilometers. Jupiter lies much farther out, orbiting at an average distance of about 5.2 astronomical units from our star. Saturn averages about 9.6. By the time we reach Neptune, the ruler has stretched to roughly 30 astronomical units. Pluto travels on a more eccentric or less circular orbit. Its average distance is about 39.5 astronomical units, although during its long 248-year orbit, it moves considerably closer to and farther from our star. At this point, we have crossed the entire region occupied by the major planets, but the solar system continues. Voyager 1 provides a useful marker beyond them. Launched from Cape Canaveral on September 5, 1977, the spacecraft passed Jupiter in 1979 and Saturn in 1980. Those planetary encounters accelerated it onto a trajectory that would eventually carry it away from the planetary region altogether. On August 25, 2012, Voyager 1 crossed the heliopause at approximately 121 astronomical units from our star. The heliopause is the boundary where the outward pressure of the solar wind, the stream of charged particles flowing from our star, becomes balanced by the surrounding interstellar medium. Crossing that boundary made Voyager 1 the first human-made spacecraft to enter interstellar space in this plasma and magnetic sense. The phrase can be misleading. Voyager had entered the environment between stars, yet it was nowhere close to another stellar system. Proxima Centauri lies roughly 268,770 astronomical units from us. Compare that with Voyager's heliopause crossing at about 121. Even after traveling for 35 years and passing beyond the region dominated by the solar wind, Voyager had covered less than 1/20th of 1% of the distance represented by the gap to Proxima Centauri. There is also a much more distant part of our own solar system that no spacecraft has reached. Far beyond the planets lies the Oort cloud, a proposed vast population of icy bodies surrounding the planetary system in a roughly spherical distribution. These objects are thought to be remnants from the formation of the solar system more than 4.5 billion years ago, and some of the long-period comets that enter the inner solar system are believed to originate there. The Oort cloud has never been photographed directly as a complete structure, and its boundaries remain uncertain. Estimates often place its inner region thousands of astronomical units away, while its outer reaches may extend tens of thousands of astronomical units farther. NASA uses a particularly useful way to express that scale. Light could require roughly 1.87 years to travel from our region to the far reaches of the Oort cloud. That is an extraordinary distance for something still gravitationally associated with our own stellar neighborhood. Yet Proxima Centauri's light takes about 4.25 years to reach us. So, even after moving beyond the Moon, every major planet, Pluto, Voyager's heliopause crossing, and the distant reservoir of comets surrounding the solar system, a substantial part of the gap to the nearest star still remains. Astronomical units work beautifully while distances are measured in tens or hundreds of them. Once the ruler stretches into hundreds of thousands, the unit begins to hide the scale almost as much as kilometers did. Astronomers needed a larger ruler, one based on the fastest thing known in physics. That ruler is the light year. A light year sounds like a measure of time because the word year is built into it. In astronomy, though, it describes distance. 1 light year is the distance light travels through space during 1 year. That distance begins with a speed almost beyond everyday experience. Light moves through a vacuum at about 299,792 kilometers every second, usually rounded to 300,000 kilometers per second. In a single second, light could travel around Earth more than 7 times. In 1 minute, it covers nearly 18 million kilometers. After 1 hour, the distance has grown to more than 1 billion kilometers. Keep that same speed going for an entire year, and the result is roughly 9.46 trillion kilometers. That is 1 light year. The usefulness of the unit becomes clear close to home. Light from our star needs a little over 8 minutes to travel the roughly 150 million kilometers between it and Earth. The Moon is close enough that reflected light takes only about 1.3 seconds to reach us. The delays grow as we move outward. At Neptune's average distance, light traveling from our star takes a little over 4 hours to reach the planet. Radio commands sent between Earth and spacecraft in the outer solar system therefore already involve delays measured in hours rather than seconds. Proxima Centauri pushes that same principle into an entirely different regime. The star is about 4.24 light-years away, meaning the light entering a telescope tonight began its journey more than 4 years earlier. A photon leaving Proxima crosses about 40 trillion kilometers before reaching our part of the galaxy. This gives stellar astronomy an unusual relationship with time. Suppose something changed dramatically around Proxima Centauri tonight. From Earth, we could not see that event tonight. The information carried by its light would still be traveling across interstellar space. More than 4 years would pass before those photons reached our telescopes. Every image of a distant object therefore shows an earlier moment in its history. For Proxima, the delay is a little over 4 years. For stars hundreds of light-years away, we see centuries into the past. A galaxy 2 million light-years away appears as it was roughly 2 million years before the light reached us. The same limit applies to every form of electromagnetic communication. Radio waves, visible light, infrared radiation, and laser signals all travel through a vacuum at the same fundamental speed. A future spacecraft at Proxima could send a message toward Earth immediately after arriving, and that message would still spend more than 4 years crossing the gap. Kilometers can describe all of these distances perfectly well. Proxima Centauri could simply be listed as roughly 40 trillion kilometers away. The problem is readability. Astronomy routinely deals with numbers so large that writing everything in kilometers produces long strings of digits that are difficult to compare. Saying that one star is 40 trillion kilometers away and another is 90 trillion kilometers away gives accurate values, but the physical relationship between them is easier to recognize as roughly 4 light-years and roughly 9.5 light-years. The light-year compresses the numbers while preserving something physically meaningful. It tells us how long light itself needs to cross the distance. That convenience also creates an easy trap for intuition. 4.24 sounds modest. The enormous scale sits inside the unit rather than in the number. Once astronomers began measuring stellar distances directly, they discovered that these enormous separations were real. For centuries, the stars had been visible every clear night, but their distances remained frustratingly difficult to measure. The breakthrough came from watching nearby stars shift by tiny amounts as Earth moved from one side of its orbit to the other. For most of human history, the stars had known positions in the sky, but almost no known distances. Astronomers could measure where a star appeared relative to a constellation and watch that position change slowly over centuries. What they lacked was a reliable way to determine how far behind the night sky each star actually sat. Earth's motion offered a solution. Over 6 months, our planet travels from one side of its orbit to the other, changing its position by almost 300 million kilometers. A nearby star viewed from those 2 locations should appear to shift very slightly against stars much farther in the background. The effect is called parallax. You can reproduce the basic geometry without a telescope. Hold one finger at arm's length and look at it using only your left eye. Then close that eye and look using your right. Your finger seems to jump sideways compared with objects across the room. Your finger has not moved. Your viewpoint has. Astronomers use the same principle on a vastly larger scale. Instead of 2 eyes separated by several centimeters, they observe from positions separated by Earth's journey around its orbit. A star measured at one time of year can then be compared with observations made about 6 months later. The size of that apparent shift reveals the distance. A nearby star produces a slightly larger parallax angle. A more distant star produces a smaller one. If the star is distant enough, the shift becomes so tiny that an instrument cannot distinguish it reliably. That was the problem astronomers faced for centuries. The nearest stars are still so remote that their annual parallax is less than 1 arcsecond. An arcsecond is an angular measurement equal to 1/3600th of a degree. Proxima Centauri's parallax is only around 3/4 of an arcsecond. That is an extremely small change in apparent position. Early telescopes simply could not measure angles like these with enough accuracy. Instruments could make stars look brighter and reveal fainter objects, but magnification alone did not solve the precision problem. Tiny distortions in lenses, atmospheric turbulence, and errors in measuring the telescope's position could all overwhelm the stellar shift astronomers were searching for. By the early 19th century, telescope design and precision measurement had finally improved enough to make the attempt practical. One of the major breakthroughs came from the German astronomer Friedrich Wilhelm Bessel. Bessel worked at the Königsberg Observatory in what was then Prussia. He concentrated on a relatively nearby star called 61 Cygni, located in the constellation Cygnus. The star was already known to move noticeably across the sky from year to year, which suggested that it might be relatively close to Earth. In 1838, Bessel announced a successful parallax measurement for 61 Cygni. he measured an annual parallax of roughly 1/3 of an arcsecond. From that tiny angle, he estimated the star's distance at a little over 10 light-years. Modern measurements place the system at roughly 11.4 light-years away. The exact 19th century value was less important than what the measurement proved. For the first time, astronomers had directly measured the distance to a star beyond our solar system using geometry. Other successful measurements followed almost immediately. Friedrich Georg Wilhelm von Struve measured Vega, and Thomas Henderson produced a distance estimate for Alpha Centauri based on observations made from the Cape of Good Hope in southern Africa. Alpha Centauri turned out to be far closer than 61 Cygni, only a little over 4 light-years away. These measurements began transforming the night sky from a flat pattern into a three-dimensional map. Some stars that appeared beside one another were actually separated by many light-years. Others that looked faint were relatively nearby, but intrinsically dim. Most importantly for our journey, the new map revealed just how much space existed between neighboring stars. The closest stellar systems were separated by trillions of kilometers, with no chain of stars filling the gaps between them. Around Earth, planets are separated by distances measured in millions or billions of kilometers. In the stellar neighborhood, those distances expand into light-years. Once the stars acquired measurable depth, the emptiness between them became impossible to ignore. That newly measured depth changed the way the night sky had to be imagined. From Earth, thousands of stars appear scattered across a single dark surface. Two stars can look almost side by side, even when one lies tens or hundreds of light-years farther away than the other. Constellations are especially good at creating this illusion. Orion looks like one recognizable arrangement, but its bright stars occupy very different distances from us. Betelgeuse lies hundreds of light-years away, while Bellatrix is much closer. The pattern exists mainly from our particular viewpoint. Once distance measurements are added, the sky becomes a three-dimensional volume, and that volume is surprisingly sparse. Our own star is enormous by planetary standards, with a diameter of roughly 1.4 million kilometers. More than 100 Earths could be placed side by side across it. Yet even an object that large becomes tiny when compared with the separation between stars. Proxima Centauri sits about 40 trillion kilometers away. The diameter of our star would fit into that gap tens of millions of times. That enormous difference between stellar size and stellar separation helps explain why direct collisions between ordinary stars are so rare in regions like our part of the Milky Way. Stars can pass through the same broad region of the galaxy for billions of years, while remaining separated by light-years. Our local neighborhood gives the scale a more concrete shape. After Proxima Centauri at roughly 4.24 light-years, the next nearby systems are already farther out. Barnard's star lies just under 6 light-years away. Wolf 359 is nearly 8 light-years from us. Sirius, the brightest star in Earth's night sky, is about 8.6 light-years away. There is no convenient line of stars between those destinations. A spacecraft heading toward Proxima would spend essentially the entire journey between stellar systems. It could not travel for 1 light-year, stop at another star, refuel and continue. The route contains no natural intermediate station. The space itself does contain matter. Hydrogen is the most common element in the interstellar medium, along with helium. Some regions also contain microscopic grains of dust made from materials such as silicates and carbon compounds. Charged particles move through the galaxy as cosmic rays, and weak magnetic fields extend across enormous distances. In some parts of interstellar space, matter exists as plasma. Plasma is gas whose atoms have been stripped of some of their electrons, leaving electrically charged particles that respond to magnetic fields. The density remains extraordinarily low. Near Earth at sea level, a cubic centimeter of air contains roughly tens of quintillions of molecules. Interstellar space can contain around 1 atom per cubic centimeter in denser diffuse regions, and considerably less in others. A spacecraft could therefore travel huge distances without encountering anything resembling an atmosphere, while still interacting occasionally with individual atoms and tiny dust grains. Gravity also helps create the geography we see. A star dominates the motion of planets and smaller bodies in its immediate neighborhood. Earth remains gravitationally bound to our star. Neptune does too, despite orbiting roughly 4.5 billion kilometers away. Even distant comets can remain weakly attached across far greater distances. Eventually, however, the gravitational influence of neighboring stars and the Milky Way becomes increasingly important. The result is a collection of compact stellar systems separated by much larger interstellar gaps. Alpha Centauri is the closest of those neighboring systems, so it can seem like the obvious first stop in any future expansion beyond our own. But reaching the nearest point in that system would not place us beside a single star surrounded by a simple family of planets. Alpha Centauri contains 3 stars, and the distances between them introduce an entirely new scale of their own. Seen from Earth, Alpha Centauri can easily sound like the name of a single star. The system is actually made of 3 stars, held together by gravity, arranged in 2 very different scales. At the center are Alpha Centauri A and Alpha Centauri B. These 2 stars form what astronomers call a binary system, meaning they orbit a shared center of mass. Each star pulls on the other continuously, and together they complete one orbit in roughly 80 years. Their separation changes considerably during that orbit, because the path is elliptical rather than perfectly circular. At their closest, Alpha Centauri A and B come within roughly 11 astronomical units of one another. At their widest separation, they can be more than 30 astronomical units apart. For comparison, Saturn orbits our star at about 9.5 astronomical units, while Neptune averages about 30. So, even the relatively close pair inside Alpha Centauri moves across distances comparable to major portions of our own planetary system. The 2 stars are also physically different. Alpha Centauri A is the larger member. It has a mass a little greater than our own star and belongs to the same broad class of yellow hydrogen-fusing stars. Its surface temperature is close to 5,800 degrees Celsius, making it similar enough to our own star that astronomers often describe it as a solar analog. Alpha Centauri B is somewhat smaller and cooler. Its mass is roughly 9/10 that of our star, and its surface temperature is around 5,200 degrees Celsius. Its light has a slightly more orange appearance than Alpha Centauri A. Together, they form the bright object traditionally known as Alpha Centauri in the southern sky. The third member is very different. Proxima Centauri is a red dwarf, the smallest and most common general type of star in the Milky Way. It has only about 12% of the mass of our star and a diameter roughly 1/7 as large. Its surface temperature is around 3,000 degrees Celsius, much cooler than Alpha Centauri A or B. Proxima is also extremely faint. Although it is the closest known star to Earth beyond our own, it cannot be seen with the unaided human eye. Its visible light output is only a tiny fraction of that produced by a star like Alpha Centauri A. Its name reflects its position. Proxima means nearest. Yet Proxima sits surprisingly far from the other 2 members of its own system. NASA material places its separation from the Alpha Centauri A and B pair at roughly 0.21 light-years. That is about 2 trillion kilometers. Light itself needs roughly 2.5 months to cross a distance of that size. Proxima is still gravitationally associated with the central pair, but its orbit operates on a completely different clock. Estimates place one complete trip around Alpha Centauri A and B at roughly 550,000 years. This kind of arrangement is known as a hierarchical triple system. Two stars form a relatively tight inner pair, while a third follows a much wider orbit around them. The structure can remain stable because the outer orbit is enormously larger than the inner one. That distinction matters when we describe Alpha Centauri as our nearest stellar system. Proxima is the nearest individual star to Earth, at roughly 4.24 light-years. Alpha Centauri A and B are slightly farther away, at about 4.37 light-years, and they are the nearest stars broadly comparable to our own. A spacecraft crossing the 40 trillion kilometers to Proxima would therefore reach only the nearest part of Alpha Centauri. Traveling onward to the bright central pair could require crossing another distance measured in trillions of kilometers. The destination that once looked like a single point has become a system with enormous internal geography. And Proxima, the smallest and faintest member of that system, became much more important in 2016 when astronomers detected evidence of a planet orbiting it. The discovery came in August 2016, when astronomers announced that Proxima Centauri was being tugged by something too small and dark to see directly. That object became known as Proxima Centauri b. The planet was detected using a technique called radial velocity. A planet does not simply circle a perfectly stationary star. Both objects orbit a shared center of mass. Because a star is much heavier, its movement is tiny, but sensitive instruments can measure that motion by watching how the star's light changes as it moves slightly toward Earth and then slightly away. When a star moves toward us, features in its spectrum shift toward shorter wavelengths. Motion away produces a shift toward longer wavelengths. Repeated changes occurring on a regular schedule can reveal the gravitational pull of an unseen planet. For Proxima Centauri, astronomers found a repeating signal lasting about 11.2 days. That remarkably short period is one of the defining characteristics of Proxima b. Earth takes 365 days to complete one orbit. Proxima b goes around its star more than 30 times during the same span. The reason is its extremely tight orbit. The planet travels at an average distance of roughly 0.0485 astronomical units from Proxima Centauri, equal to about 7 million kilometers. Mercury, the innermost planet in our own solar system, averages almost 58 million kilometers from our star. A planet orbiting that close to a star might sound unbearably hot. Proxima Centauri changes that calculation because it is a small, relatively cool red dwarf producing far less light than our own star. Current estimates place Proxima b at roughly 1.06 Earth masses, meaning its minimum measured mass is very close to Earth's. That makes it an especially interesting object among nearby exoplanets, the general term for planets orbiting stars beyond our solar system. Its orbit also places it within what astronomers call the habitable zone. That phrase has a very specific meaning. The habitable zone is the range of distances where a planet could potentially maintain liquid water on its surface if its atmosphere and other conditions are suitable. It does not tell us that liquid water is actually present. It also does not tell us whether the planet has an atmosphere, oceans, continents, or life. Those details remain largely unknown for Proxima b. Its star creates one of the biggest uncertainties. Red dwarfs can remain active for extremely long periods, and Proxima Centauri regularly produces stellar flares. These are sudden releases of magnetic energy that send intense radiation outward from the star. Because Proxima b orbits only about 7 million kilometers away, the planet sits much closer to those events than Earth does to activity from our own star. Powerful ultraviolet and X-ray radiation can affect atmospheric chemistry. Over very long periods, repeated stellar activity may also help strip atmospheric gases away, especially if a planet lacks a strong magnetic field or a sufficiently massive atmosphere. Researchers, therefore, cannot infer habitability simply from orbital distance. Proxima b could possess conditions allowing liquid water somewhere on its surface. It could have lost much of its atmosphere. A dense atmosphere might distribute heat around the planet differently from anything seen on Earth. Present observations do not yet distinguish confidently among possibilities like these. Its orbit may create another important effect. A planet this close to a low-mass star can experience strong tidal forces. Over time, those forces may slow its rotation until the same hemisphere continually faces the star, a state called tidal locking. Whether Proxima b is fully locked depends on its orbital history and internal dynamics, so this remains an area of modeling rather than direct observation. None of that reduces the scientific value of the planet. In some ways, the uncertainty increases it. Across roughly 40 trillion kilometers sits a planet close to Earth's mass, orbiting the nearest star beyond our own system. We know its year lasts only 11.2 days. We can estimate how strongly Proxima pulls on it and how much energy reaches its orbit. Its surface remains beyond the resolving power of our current telescopes. A close spacecraft encounter could measure that world from inside the system rather than from more than 4 light-years away. The destination is therefore real, measurable, and scientifically compelling. Getting a machine there exposes just how little our fastest spacecraft speeds matter once the journey is measured in light-years. Voyager 1 gives us the most realistic example of what a human-built spacecraft can do once it has finished using planets for acceleration and begins a long coast through interstellar space. The spacecraft left Earth on September 5, 1977. After encounters with Jupiter in 1979 and Saturn in 1980, it was placed on a trajectory that would carry it permanently away from the planetary region. Today, Voyager 1 moves relative to our star at roughly 17 kilometers per second. That is about 61,000 kilometers per hour. Inside the solar system, a speed like that is extraordinary. At 17 kilometers per second, a spacecraft could cross the average Earth-Moon distance in a little over 6 hours if it were traveling directly between them at a constant speed. Applied to Proxima Centauri, the same velocity produces a completely different result. The distance is roughly 40.2 trillion kilometers. Dividing that distance by 17 kilometers per second gives a travel time of around 75,000 years. This is only a comparison. Voyager 1 is not headed toward Proxima Centauri, and the motions of both the spacecraft and nearby stars would matter over such a long period. The calculation shows what a genuine interstellar coasting speed looks like when placed beside the nearest star distance. 75,000 years is far beyond the lifetime of any spacecraft civilization has attempted to maintain. Voyager has operated for less than 50 years, already making it one of the longest-lived machines ever sent into space. A second spacecraft gives us the opposite extreme. Parker Solar Probe was launched in August 2018 to study the outer atmosphere of our star from extraordinarily close range. The mission repeatedly uses the gravity of Venus to reshape its orbit, allowing Parker to pass closer and closer to the star while gaining enormous orbital speed. During its closest passes, Parker has reached roughly 692,000 kilometers per hour. In June 2026, it again matched that record, remaining the fastest human-made object ever built. At that velocity, Parker travels more than 11,000 kilometers every minute. Now place that speed against the same 40.2 trillion kilometer gap. If a spacecraft could somehow move directly toward Proxima Centauri at Parker's peak velocity and maintain that speed continuously, the crossing would still take roughly 6,600 years. That number needs an important qualification. Parker does not possess an engine capable of accelerating it to 692,000 kilometers per hour and then sending it wherever engineers choose. Its record speed comes from the particular orbit created by the gravity of our star. As Parker falls inward, gravitational potential energy is converted into motion. Near its closest approach, the spacecraft is moving extremely quickly because it is deep inside that gravitational field. After passing closest approach, Parker climbs outward again and slows. So Parker cannot simply turn toward Alpha Centauri and carry its record-setting speed into interstellar space. Using that velocity here gives us a deliberately generous comparison, a way of asking what would happen if humanity's fastest measured spacecraft speed could somehow be preserved for the entire journey. The answer remains thousands of years. The contrast between Voyager and Parker also shows why small improvements to current spacecraft technology cannot solve the problem. Voyager gives us a real long-term interstellar coast and produces a journey measured in tens of thousands of years. Parker increases the comparison speed by more than an order of magnitude, yet the result still spans thousands of years. Bringing the crossing into decades requires velocities hundreds or thousands of times beyond the speeds at which our deep space probes normally travel. At that point, adding a larger fuel tank or building a slightly stronger rocket stops being enough. The propulsion system itself has to operate according to a very different set of physical limits. And the reason begins with an inconvenient fact about rockets. Every kilogram of fuel they carry must also be accelerated. The most obvious way to make a spacecraft faster is to give it more fuel. That approach works well enough when the destination is a planet or moon. Across interstellar distances, the fuel itself becomes part of the problem. A rocket moves by throwing mass backward at high speed. Hot exhaust leaves the engine in one direction, and the spacecraft gains momentum in the other. The faster the exhaust can leave, and the more propellant the vehicle can use, the greater the change in velocity the rocket can achieve. Adding propellant sounds straightforward until its mass is included. Suppose a spacecraft carries an additional ton of fuel. The engines must accelerate that ton, along with the spacecraft. More propellant is then required to accelerate the additional fuel. Increasing the desired speed causes this cycle to grow rapidly, with much of the vehicle eventually devoted to moving propellant that will later be discarded. This relationship is described by the Tsiolkovsky rocket equation, named after Konstantin Tsiolkovsky, the Russian scientist who published the principle in 1903. The equation connects three things: how much a spacecraft can change its velocity, how quickly its engine throws exhaust backward, and the ratio between the spacecraft's mass before and after its propellant is burned. That last quantity is called the mass ratio. Imagine a rocket that weighs 100 tons fully fueled, and 10 tons once its tanks are empty. Its mass ratio is 10 to 1. Increasing that ratio provides additional velocity, but each new increase becomes harder, because the extra propellant also has to be accelerated during the earlier part of the flight. The result is an exponential penalty. Chemical rockets encounter this limit especially quickly, because their exhaust velocities are relatively low compared with the velocities needed for interstellar travel. A powerful hydrogen and oxygen rocket engine can produce exhaust moving at only a few kilometers per second. The exact value depends on engine design and operating conditions, But even the best chemical systems remain enormously below the tens of thousands of kilometers per second needed to cross 4 light-years within a few decades. The difference is rooted in chemistry itself. Chemical rocket engines release energy by rearranging electrons between atoms and molecules. Burning hydrogen with oxygen produces hot water vapor and releases a large amount of energy by everyday standards. Nuclear reactions operate on a much deeper level inside atomic nuclei and can release millions of times more energy per unit mass than ordinary chemical reactions. No amount of clever engineering can make a chemical bond contain nuclear quantities of energy. This creates an important distinction between leaving Earth and traveling between stars. Escaping Earth's gravity requires reaching an escape velocity of about 11.2 kilometers per second near the surface, although real launches build velocity gradually and suffer additional losses from gravity and atmospheric drag. Modern launch vehicles can accomplish this by using several stages, dropping empty tanks and engines as they climb. An interstellar spacecraft intended to reach Proxima Centauri in 40 years would need an average speed around 10% of light speed, roughly 30,000 kilometers per second, before accounting for acceleration and deceleration. That target is thousands of times greater than the velocity associated with escaping Earth. Even reaching 1% of light speed means traveling close to 3,000 kilometers per second. At that velocity, the 40 trillion kilometer crossing would still take more than 400 years. The rocket equation therefore explains why building a larger version of today's launch vehicles cannot simply solve Alpha Centauri. Chemical rockets are excellent at placing satellites into orbit, sending robotic missions toward planets, and accelerating spacecraft onto trajectories through the solar system. Their underlying energy source places practical interstellar speeds far outside the range they were built to reach. By the middle of the 20th century, engineers studying interstellar travel were already confronting this limitation directly. Some began replacing chemical reactions with nuclear energy. Others eventually considered fusion, using the same basic process that powers stars. The machines they proposed became far more extreme than anything that had ever left Earth. By the late 1950s, some engineers were already treating the limits of chemical propulsion as a reason to explore far more energetic systems. One of the earliest serious examples was Project Orion. Work began in 1958 under a team that included physicist Freeman Dyson and mathematician Stanislaw Ulam. The concept explored nuclear pulse propulsion, using repeated nuclear energy releases behind a spacecraft to provide thrust far beyond what chemical engines could produce. The attraction came from energy density. Chemical rockets release energy through reactions involving electrons in atoms and molecules. Nuclear reactions involve the atomic nucleus itself. A relatively small amount of nuclear fuel can therefore release vastly more energy than the same mass of chemical propellant. That difference offered engineers something conventional rockets could not provide: much higher potential spacecraft velocities without requiring an impossibly large chemical fuel load. Project Orion studies considered vehicles ranging from planetary spacecraft to much larger concepts intended for extremely high-speed missions. Some designs were enormous, with masses measured in thousands of tons. They required technologies, infrastructure, and political conditions that never came together. The Partial Test Ban Treaty of 1963 also prohibited nuclear explosions in the atmosphere, underwater, and in outer space, removing one of the environments in which an Orion-style system would have operated. The project ended during the 1960s, but the underlying lesson remained important. Once engineers tried to design spacecraft capable of traveling far beyond the solar system, chemical propulsion quickly gave way to nuclear ideas. A more focused interstellar study appeared about a decade later. In 1973, the British Interplanetary Society began Project Daedalus. 13 researchers spent 5 years developing a detailed conceptual spacecraft capable of reaching another star, using technology they believed might eventually become achievable. Their destination was Barnard's star, a red dwarf roughly 6 light-years away. The Daedalus design relied on fusion. Fusion is the process in which light atomic nuclei combine into heavier nuclei and release energy. It is the same general physical process that powers stars. For a spacecraft, the attraction is again energy density. Fusion fuel could theoretically produce exhaust moving vastly faster than the gases expelled from chemical rocket engines. Daedalus proposed a technique called inertial confinement fusion. Tiny fuel pellets would be compressed and heated until fusion occurred, producing high-energy material that could be directed backward to accelerate the spacecraft. The resulting design was immense. Daedalus was conceived as an uncrewed 2-stage probe with an initial mass of tens of thousands of tons, most of it fuel. The first propulsion stage would operate for about 2 years. A second stage would continue accelerating afterward, bringing the total powered acceleration period to roughly 3.8 years. By the end of that acceleration, the spacecraft was intended to reach more than 12% of the speed of light. That is over 36,000 kilometers per second. At that speed, Daedalus could have crossed the distance to Barnard's star in roughly 46 years. A journey that would take present-day spacecraft tens of thousands of years had been reduced, at least on paper, to less than half a century. The design still carried an important limitation. Daedalus was planned as a flyby mission. It did not carry enough capability to decelerate from its interstellar cruise speed and enter orbit around Barnard's star. After decades of travel, it would pass through the system at enormous velocity, gather observations during the encounter, and continue onward. Neither Orion nor Daedalus became a spacecraft. Humanity has never constructed an interstellar fusion engine, and many of the materials, fuel production systems, and engineering capabilities required by Daedalus remain beyond what exists today. Their importance comes from what the studies demonstrated. Once interstellar distances are taken seriously, the proposed machines become dramatically different from ordinary rockets. Engineers began looking toward nuclear energy because crossing several light-years within decades requires velocities that chemistry cannot conveniently provide. Daedalus tried to solve the problem with a powerful fusion spacecraft weighing thousands of tons. A much newer idea approaches the same 40 trillion kilometer gap from the opposite direction. Instead of making the engine enormously more powerful, it makes the spacecraft extraordinarily small. Breakthrough Starshot takes the interstellar problem and reduces the mass of the spacecraft until an entirely different propulsion method becomes possible. The project was announced in April 2016 as part of the Breakthrough Initiatives. Its long-term goal is to demonstrate technology that could eventually send extremely small robotic probes toward Alpha Centauri within a few decades. The proposed spacecraft would bear little resemblance to Voyager, Parker Solar Probe, or the enormous Daedalus design. At the center of the concept is a tiny electronic package, sometimes described as a star chip. The payload could weigh only a few grams while carrying miniature cameras, sensors, processors, and communication equipment. Attached to it would be a thin reflective sail measuring several meters across. The sail provides the propulsion surface. Light consists of particles called photons. Photons have no rest mass, but they carry momentum. When light strikes a reflective surface and bounces away, it transfers a very small amount of momentum to that surface. Sunlight can produce this effect naturally, and spacecraft have already demonstrated solar sailing. Starshot would increase the force enormously by replacing ordinary sunlight with a concentrated beam produced by a powerful laser array. The energy source would remain near Earth rather than traveling aboard the spacecraft. That changes the mass problem described by the rocket equation. A conventional rocket must carry the propellant it plans to use later. A beamed light sail receives energy from somewhere else, allowing most of the fuel tanks, engines, and reaction mass to disappear from the vehicle. Starshot studies have proposed a large array containing many individual laser emitters working together. The combined beam would be aimed at the reflective sail while the probe remained relatively close to Earth. The acceleration would be intense. Instead of operating an engine continuously for years, the laser system could accelerate the tiny craft for only several minutes. During that short period, the probe would gain thousands of kilometers per second until it approached a proposed cruise speed of roughly 20% of light speed. That is around 60,000 kilometers per second. At that velocity, a spacecraft would cover the average Earth-Moon distance in only a few seconds. The distance that Voyager would need roughly 75,000 years to cross could theoretically be covered in a little over 20 years. For the first time in our journey, Alpha Centauri begins to fit inside an ordinary human lifetime. Someone could watch the probe's launch and still be alive when they reach the system decades later. The price of that speed appears in the spacecraft's extreme size restrictions. A few grams can be accelerated much more easily than tons of machinery. Every additional component increases the energy required from the laser and adds stress to the sail during acceleration. Miniaturization, therefore, has to reach extraordinary levels. Cameras, navigation systems, computers, power supplies, and communication equipment would all have to function inside a package with a mass comparable to a small electronic device. Starshot has also proposed sending many probes rather than relying on a single spacecraft. Thousands of inexpensive nanocraft could provide redundancy. Some could fail during acceleration or during the long crossing, while others continued toward the destination. Nothing comparable to a complete Starshot mission exists today. Building the laser array, manufacturing sails able to survive the acceleration, maintaining precise beam control, and returning useful data across more than 4 light-years all remain major engineering challenges. Still, the concept demonstrates something important about the distance to the nearest star. Reducing travel time from thousands of years to decades does not necessarily require a gigantic spacecraft. Physics also allows an approach in which the payload becomes extremely light and the propulsion energy stays behind. At roughly 20% of light speed, however, the journey enters a velocity range humanity has never experienced with a spacecraft. The thin gas and microscopic dust scattered through interstellar space begin to matter very differently when the vehicle meets them at 60,000 kilometers per second. At roughly 60,000 kilometers per second, the thin material between the stars begins to behave very differently. Earlier, the interstellar medium looked almost empty. In many regions, only a few atoms occupy each cubic centimeter of space, accompanied by much rarer grains of dust. A conventional spacecraft, moving through such an environment, encounters very little resistance. A probe traveling at 20% of light speed experiences those same particles with enormously greater collision energy. The basic reason is kinetic energy, the energy an object has because it is moving. At everyday speeds, a microscopic grain of dust carries almost no noticeable energy. Increase its relative velocity to tens of thousands of kilometers per second, and an impact can heat, melt, or remove material from a spacecraft's surface. Distance makes the problem accumulate. A Starshot probe would spend a little over 20 years crossing more than 40 trillion kilometers. Even if each cubic centimeter of space contains very little matter, the spacecraft passes through an immense column of that material during the journey. Researchers examined this problem directly in 2016. A study led by astronomer Thiem Hoang modeled how gas atoms and interstellar dust could affect a spacecraft traveling at roughly 0.2 times the speed of light, close to the velocity envisioned for breakthrough Starshot. The gas and dust create different kinds of damage. Individual atoms of hydrogen and helium strike the leading surface in enormous numbers. At relativistic speeds, those particles can penetrate exposed material and deposit energy beneath the surface. Repeated bombardment can gradually alter or erode the material over the course of the crossing. Dust grains are far less common, but each grain contains vastly more mass than an individual atom. When one of those grains strikes at around 60,000 kilometers per second, its energy is concentrated into a tiny area. The modeled results showed that impacts could create local melting and small craters while gradually wearing away the forward-facing surface. Under one modeled set of interstellar conditions, the researchers estimated that dust erosion could remove roughly 0.5 millimeter of material during a journey comparable to the crossing toward Alpha Centauri. 0.5 millimeter sounds insignificant on an ordinary spacecraft. For a vehicle whose total mass may be measured in grams, it becomes a serious engineering consideration. The exact amount of damage depends on several uncertain factors. Different materials respond differently to high-energy impacts, and the density of gas and dust is not perfectly uniform throughout nearby interstellar space. The path toward Alpha Centauri may contain regions that are cleaner or more crowded than others. Engineers can protect the spacecraft by placing shielding on the side facing forward. That solution immediately reconnects the problem to mass. A thick protective layer is easy to imagine on a probe weighing hundreds of kilograms. Starshot gains its extraordinary acceleration precisely because the craft is so light. Adding shielding means the laser must accelerate more mass, while every gram devoted to protection leaves less available for cameras, communications equipment, and other spacecraft systems. Orientation also becomes important. The narrowest or most heavily protected surface could face the direction of travel during the long cruise, reducing the area exposed to incoming particles. Even then, the probe would spend decades moving through an environment no spacecraft has ever experienced at anything close to the proposed speed. Voyager encounters interstellar particles at roughly 17 kilometers per second. A Starshot-style craft would meet them at around 60,000 kilometers per second. The same sparse medium becomes a fundamentally different engineering environment when relative velocity rises by thousands of times. That creates the first major cost of reducing the Alpha Centauri journey to a human timescale. Speed solves the calendar problem while making microscopic matter capable of damaging the vehicle carrying our instruments. And a probe that survives those impacts still has to arrive at the correct location. During more than 20 years of flight, Proxima Centauri will keep moving through the galaxy, carrying its planets with it. The position we measure for Proxima Centauri is already old by the time its light reaches Earth. At a distance of about 4.24 light-years, every telescope observation shows the star where it was more than 4 years earlier. During that interval, Proxima has continued moving through the Milky Way, along with the rest of the Alpha Centauri system. Stars are never perfectly fixed against space. Each one travels through the galaxy with its own three-dimensional velocity. Part of that motion can carry a star closer to or farther from us. Another part changes its apparent position across the sky. Astronomers call that sideways component proper motion. Proxima Centauri has unusually large proper motion because it is so close to Earth. From year to year, careful measurements show it shifting across the background of much more distant stars. That motion is slow to the eye, yet it becomes important when planning a journey lasting decades. A spacecraft aimed at the position where Proxima appears today would be using information that is already more than 4 years old. By the time a 20-year mission arrived, the entire system would have moved farther along its path. Mission planners therefore need an intercept trajectory. An intercept means aiming for the location where the target and spacecraft are expected to arrive at the same time. Engineers already use this principle throughout the solar system. A probe traveling to Mars is directed toward the future position of Mars rather than the place where the planet appears at launch. Interstellar navigation stretches the same calculation across trillions of kilometers and decades of motion. Astronomers can measure Alpha Centauri's position, proper motion, and motion toward or away from Earth with great precision. Those measurements allow computers to predict where the system should be when a spacecraft reaches the area. Small uncertainties still matter because the distance magnifies them. Imagine changing a spacecraft's direction by only a tiny fraction of a degree shortly after launch. Close to Earth, the resulting difference in position may be small. After traveling roughly 40 trillion kilometers, the two paths can end up separated by an enormous distance. At Alpha Centauri, even missing by 1 astronomical unit would place the probe about 150 million kilometers from its intended point. That would be especially costly for a fast flyby mission. A craft moving at 20% of light speed crosses 1 astronomical unit in only about 42 minutes. There would be very little time to recover from a major targeting error near arrival. The probe would therefore need some ability to navigate for itself. Cameras could compare observed star positions with stored maps. Onboard computers could estimate the spacecraft's trajectory and command small corrections during the cruise. As Alpha Centauri grew closer, the craft could use the stars and perhaps bright objects within the system as increasingly precise navigation references. Autonomy becomes important because instructions from Earth cannot arrive quickly. Halfway through the journey, a signal already needs years to cross the remaining distance. Near Alpha Centauri, a correction ordered from Earth would still take more than 4 years to reach the spacecraft. By then, a probe traveling at 60,000 kilometers per second would have covered many trillions of kilometers. The mission therefore has to predict far ahead, measure its own position, and correct its course without waiting for immediate help from controllers on Earth. Interstellar navigation combines two kinds of uncertainty that rarely feel significant in ordinary travel. The destination moves, while the vehicle crosses the gap, and very small directional errors can grow into distances comparable to entire planetary systems. Even perfect navigation, however, only guarantees that the spacecraft passes through the right place. At 20% of light speed, arriving at Alpha Centauri and remaining there are completely different engineering problems. After a little more than 20 years of flight, a Starshot-like probe could finally enter the Alpha Centauri region. Its speed would still be close to 20% of the speed of light, roughly 60,000 kilometers per second. That number makes the meaning of arrival very different from a planetary mission. At 60,000 kilometers per second, the probe would cross 1 astronomical unit, about 150 million kilometers, in roughly 42 minutes. It could traverse a distance comparable to the average separation between Earth and our star in less than an hour. That leaves very little time for close observations. A probe passing Proxima b might begin collecting its most valuable measurements days before closest approach, then race through the immediate planetary region in a matter of hours. Cameras and other instruments would have to work automatically, recording as much as possible while the geometry changed extremely quickly. This is why the basic breakthrough Starshot concept is usually described as a flyby mission. The spacecraft would enter the Alpha Centauri system at enormous speed, observe whatever targets it could reach along its path, and continue outward afterward. It would not simply arrive and settle into orbit around Proxima Centauri or one of its planets. Remaining in the system requires removing most of the velocity gained at departure. Orbital capture happens when a spacecraft slows enough for the gravity of a planet or star to keep it bound. Space agencies perform versions of this maneuver routinely within our solar system. A spacecraft approaching Mars, for example, can fire its engine to reduce its speed relative to the planet, allowing Martian gravity to bend its path into an orbit. Interstellar speeds make the same principle much harder. A probe arriving at 60,000 kilometers per second would need to lose an extraordinary amount of velocity before Proxima's gravity could capture it into anything resembling a conventional orbit. Carrying fuel for that braking maneuver creates many of the mass problems encountered earlier. The spacecraft must accelerate the braking system during departure and carry it across 4 light-years before using it. More propellant means more launch mass, which demands more energy from the propulsion system that accelerated the vehicle in the first place. Researchers have explored ways to slow interstellar probes without carrying a large conventional fuel supply. One proposed method is a magnetic sail. The spacecraft would generate a magnetic field that interacts with charged particles in the surrounding plasma. Over a sufficiently long distance, those interactions could gradually reduce the craft's speed. Other studies have examined using light from the destination stars themselves. A large reflective sail approaching Alpha Centauri could, in principle, orient itself so that incoming photons push against its motion and provide some braking. Ideas like these remain technically demanding. A sail large enough to provide useful deceleration must survive decades of travel and deploy or remain intact at the destination. Magnetic braking requires lightweight systems capable of producing useful fields while operating far from Earth. The amount of deceleration needed also depends on the mission. A brief scientific flyby can tolerate enormous arrival speed. A probe intended to spend years studying Proxima b from nearby would need a much slower encounter. A spacecraft meant to enter orbit would face an even stricter requirement. So the fastest route to Alpha Centauri may produce the shortest visit. After crossing roughly 40 trillion kilometers, the first human-made object to reach another stellar system could pass through its most interesting region in hours and then continue into interstellar space. That limitation points towards something deeper than propulsion design. Every increase in speed requires energy. Removing that speed requires dealing with energy again. Once the journey reaches a significant fraction of light speed, the amounts involved become enormous. The difficulty of slowing an interstellar spacecraft begins with the energy it acquired before the journey even started. Acceleration gives a moving object kinetic energy. That energy remains with the spacecraft during its coast through interstellar space. If the mission eventually needs to slow down, some mechanism must remove or redirect a large portion of it. At ordinary speeds, kinetic energy depends on 2 things: mass and velocity. Mass contributes directly. Double the mass of an object moving at the same speed, and its kinetic energy doubles. Velocity has a much stronger effect because it appears squared in the classical equation. Doubling the speed produces 4 times the kinetic energy. Increasing the speed by a factor of 10 produces 100 times as much. This is one reason an interstellar mission becomes dramatically harder as its desired travel time falls. A spacecraft moving at 1% of light speed travels close to 3,000 kilometers per second. Reaching 10% means roughly 30,000 kilometers per second. 20% brings the speed to about 60,000 kilometers per second. Each increase shortens the crossing, while the energy requirement rises much faster than the velocity itself. Mass then multiplies the problem. Consider a 1-gram probe traveling at 20% of light speed. Even such a tiny spacecraft would carry an enormous amount of kinetic energy compared with objects moving at familiar speeds. Now, increase the spacecraft mass to 1 kilogram while keeping the velocity unchanged. The kinetic energy becomes 1,000 times greater. A ton contains 1 million grams, so a 1-ton spacecraft moving at the same speed carries 1 million times the kinetic energy of the original 1-gram probe. That scaling is central to breakthrough Starshot. Its gram-scale spacecraft are not simply miniature because small electronics are convenient. Every gram removed from the probe directly reduces the energy required to accelerate it. The laser array still faces an extraordinary task, but the calculation becomes far more manageable than accelerating a conventional spacecraft weighing tons. The numbers become even less forgiving as velocity approaches the speed of light. At lower speeds, the classical kinetic energy equation provides an excellent approximation. Once a spacecraft reaches a substantial fraction of light speed, special relativity has to be included. Special relativity describes how measurements of time, distance, momentum, and energy behave for objects moving at extremely high velocities. One important consequence is that the energy required to continue accelerating a massive object rises increasingly steeply as its speed approaches that of light. A spacecraft can continue getting closer to light speed, but each additional increase demands more energy than the classical equation would predict. At 20% of light speed, relativistic corrections are present but still fairly modest. At 90%, they become impossible to ignore. The energy curve becomes increasingly severe as the spacecraft moves closer to the physical limit. Braking carries the same burden in reverse. If a probe arrives with enormous kinetic energy, entering orbit requires removing enough of that motion for the destination's gravity to capture it. A flyby avoids much of that requirement because the spacecraft simply keeps the energy and continues onward. That is why fast interstellar travel repeatedly returns to the same physical quantity. The 40 trillion kilometers between Earth and Proxima Centauri do not consume energy merely by existing. A probe could cross them slowly, with relatively modest propulsion demands, if enough time were available. Trying to compress that journey into decades changes everything. Speed requires energy, and carrying more mass requires proportionally more of it. Once the payload grows from a few grams into the machinery needed to support a person, the scale of the mission changes almost immediately. A gram-scale probe can cross interstellar space because almost everything about it has been stripped down to the smallest possible mass. Sending a person changes that calculation immediately. An adult human typically has a mass measured in tens of kilograms. Even before adding a seat, clothing, instruments, or a pressure vessel, the passenger alone may outweigh a 1-gram Starshot probe by 70,000 times or more. The spacecraft then has to keep that passenger alive. Humans need breathable air with carefully controlled oxygen and carbon dioxide levels. On a journey lasting decades, carrying fresh air for the entire trip would be impractical. So much of it would have to circulate through a life support system that continually removes carbon dioxide and restores usable oxygen. Water creates a similar problem. A person can consume several liters each day through drinking, food preparation, and basic hygiene. Over 20 years, even modest daily consumption would add up to many tons if every liter had to be launched from Earth. A realistic interstellar habitat would therefore need extremely efficient water recovery, capturing moisture from cabin air and recycling wastewater repeatedly. The International Space Station already demonstrates parts of this approach. Its environmental systems recover water and regenerate cabin air, reducing how much material has to be delivered from Earth. An interstellar crew would lose the possibility of regular supply missions. Food would have to last for years or be produced partly aboard the spacecraft. Temperature control equipment would continuously move waste heat away from electronics and living areas. Medical supplies would need to cover conditions that could develop far beyond any hospital. Radiation protection adds substantial mass. Earth's atmosphere and magnetic field shield people from much of the radiation arriving from space. A spacecraft between stars would spend years outside that protection, exposed to energetic particles from the galaxy and activity from stars. Water, specialized materials, and structural shielding can absorb some of that radiation, but protection becomes another item the propulsion system has to accelerate. Reliability creates a second layer of difficulty. A 20-year spacecraft cannot depend on every pump, valve, computer, and air processing unit working perfectly for the entire mission. Important systems would need backups, replacement parts, and ways for the crew to make repairs. That redundancy increases survival chances while also increasing mass. Long exposure to very low gravity could create additional complications. Astronauts living for months in orbit experience loss of bone and muscle unless they exercise extensively. Some crude interstellar concepts therefore use rotating habitats. Rotation can create an effect similar to gravity by continually pushing occupants toward the outer wall of a spinning structure. Producing a comfortable artificial gravity environment requires a habitat large or fast enough for the rotation to be tolerable. Larger rotating structures need more material, stronger supports, bearings or other moving systems, and additional engineering margin. Every one of these solutions eventually returns to the same physical problem. A kilogram of water has to reach interstellar speed. So does a kilogram of radiation shielding. The same applies to food, structural material, spare equipment, and the machinery keeping the cabin habitable. At 20% of light speed, each added kilogram carries the kinetic energy associated with roughly 60,000 kilometers per second of motion. A robotic flyby probe can therefore become plausible long before a crewed spacecraft does. Both may be described as missions to Alpha Centauri, yet their engineering scales are separated by enormous differences in mass, energy, and reliability. Humanity may someday build machines capable of carrying people across that distance. Even if every life support and propulsion problem were eventually solved, one feature of the journey would remain unchanged. Information itself would still need more than 4 years to cross the gap. More than 4 years separates Alpha Centauri from Earth, even when nothing with mass has to make the journey. Radio waves and laser signals are forms of electromagnetic radiation, so they travel through a vacuum at the speed of light. For Proxima Centauri, about 4.24 light-years away, that creates a communication delay of more than 4 years in each direction. A message transmitted from Earth tonight would reach the system sometime more than 4 years from now. If someone near Proxima received it and answered immediately, their reply would need another 4.24 years to return. The full exchange would therefore take more than 8.5 years. That delay is built directly into the distance. Larger antennas could improve reception. More powerful transmitters could make a signal easier to detect. Better computers could compress information more efficiently. None of those improvements can make the signal cross interstellar space faster than light. Space agencies already work with smaller versions of this problem. Mars can be far enough from Earth that a radio signal takes more than 20 minutes to travel one way. Controllers cannot steer a rover around a rock using a joystick and watch the result instantly. Commands are prepared in advance, transmitted across space, and then carried out by the rover's onboard computers. At Proxima Centauri, the same basic problem stretches from minutes into years. A high-speed interstellar probe would need extensive autonomy. Its cameras and navigation instruments would have to recognize targets, choose when to make observations, manage its power, and respond to unexpected conditions without waiting for instructions from Earth. During a rapid flyby, this independence becomes essential. A probe moving at roughly 20% of light speed could cross 1 astronomical unit in about 42 minutes. By the time Earth received information describing a problem near Proxima, more than 4 years would already have passed. The spacecraft would be far beyond the system. Breakthrough Starshot therefore faces a communication challenge alongside its propulsion problem. The proposed nanocraft may weigh only a few grams, leaving very little mass for a transmitter or power source. After traveling for a little over 20 years, the probes would need to send scientific information across roughly 40 trillion kilometers toward receivers near Earth. Their signals would weaken enormously as they spread through space. Engineers have studied laser communication because a narrow beam can concentrate energy much more effectively than a signal radiated broadly in every direction. Even then, pointing a tiny transmitter accurately across more than 4 light-years while operating with limited onboard power is a demanding task. The schedule of discovery would also be unusual. Suppose a Starshot-style probe completed its crossing in about 21 years and successfully photographed Proxima b during its encounter. Earth would not receive those images at the moment they were taken. The data would begin another journey, lasting more than 4 years. A launch, followed by a 21-year crossing, could therefore place the first returned observations roughly 25 years or more after departure, depending on the exact mission trajectory and transmission schedule. Human travelers would face the same delay. An expedition at Alpha Centauri could send recordings, scientific results, family messages, and news back toward Earth. Each transmission would describe events already more than 4 years old when received. Ordinary conversation would disappear across that distance. Someone on Earth asking a simple question could wait more than 8 years to receive an answer, even if the recipient responded immediately. Major events on either side would remain unknown to the other for years. The nearest possible stellar settlement would therefore exist within communication range, yet outside anything resembling real-time contact. Special relativity changes how time can pass for travelers moving at extreme speed, which seems to offer one remaining way to soften the journey. Its effect becomes important only when the spacecraft begins moving much faster than the Starshot speeds considered so far. At 20% of light speed, the spacecraft has entered relativistic territory, but only barely. Special relativity predicts that 2 observers moving rapidly relative to one another can measure different amounts of elapsed time. A clock traveling aboard the spacecraft can accumulate slightly less time than a clock that remains on Earth. The effect is called time dilation. Physicists describe its strength using a number called the Lorentz factor. At everyday speeds, that factor is so close to 1 that the difference cannot be noticed without extremely precise instruments. Even at the velocity proposed for breakthrough Starshot, about 20% of light speed, the Lorentz factor is only around 1.02. Imagine a simplified journey lasting 20 years as measured from Earth, while the spacecraft spends almost all of that time moving at the same speed. The clock aboard the craft would record only modestly less time. Relativity would shave months from the traveler's experience rather than transforming decades into a short voyage. Meaningful time compression begins much closer to light speed. At 90% of light speed, a spacecraft would move at roughly 270,000 kilometers per second. The Lorentz factor rises to about 2.29. That means a long cruise measured from Earth could feel less than half as long to travelers aboard the moving spacecraft, once acceleration and braking are set aside for the comparison. A 40-year interval in Earth's frame would correspond to roughly 17.5 years for someone coasting at that velocity. Push the speed to 99% of light speed, and the effect becomes much more dramatic. The Lorentz factor is then about 7.09. During a long, constant speed portion of a journey, 7 years measured in Earth's frame would correspond to roughly 1 year aboard the spacecraft. This is a genuine consequence of physics. Particle accelerators measure the same effect routinely. Fast-moving, unstable particles can survive longer from the laboratory's point of view because their internal clocks experience less elapsed time. The difficulty appears in what it takes to reach those velocities. Going from 20% of light speed to 90% requires far more than increasing the propulsion system by a factor of 4.5. Relativistic energy rises steeply as velocity approaches light speed. A spacecraft with mass can be accelerated closer and closer to that limit, but reaching light speed itself would require an unlimited amount of energy. The hazards encountered earlier also become more severe. At 20% of light speed, microscopic dust already threatens a lightweight probe. At 90%, the relative energy of collisions becomes vastly greater. Individual particles of interstellar gas strike the spacecraft with energies that create much more demanding shielding problems. Navigation also becomes less forgiving because the vehicle covers enormous distances in very short periods. At 90% of light speed, 1 astronomical unit passes beneath the spacecraft in a little over 9 minutes. Deceleration becomes correspondingly harder. A vehicle arriving near Alpha Centauri at 99% of light speed carries an extraordinary amount of kinetic energy that must somehow be removed if the mission intends to remain there. Increasing shielding adds mass, and greater mass raises the energy required for acceleration. Equipment needed for braking creates the same coupling. A crewed vehicle would magnify every one of these requirements further. Relativity, therefore, provides a real reduction in traveler time, but the useful effects become large only after the spacecraft enters a velocity range far beyond anything humanity can currently approach with macroscopic objects. Starshot's proposed 20% of light speed is already extraordinarily ambitious. 90 or 99% would demand an entirely different level of energy, protection, propulsion, and control. Even if future engineering eventually makes such velocities possible, crossing the interstellar gap would only deliver the spacecraft into another enormous landscape. Alpha Centauri itself stretches across distances large enough that reaching its nearest star would still leave much of the system far away. Most discussions of travel to the nearest star naturally focus on Proxima Centauri because it is the closest member of the system to Earth. A spacecraft that successfully crosses roughly 4.24 light-years would therefore reach Proxima's neighborhood first. That still leaves an enormous distance to Alpha Centauri A and B. Proxima orbits far outside the central pair, at a separation of roughly 0.21 light-years. That works out to about 2 trillion kilometers. Light itself needs around 2.5 months to travel that distance. For comparison, light from Earth reaches Neptune in only a few hours. Even after reaching another stellar system, traveling from its outer member to its central stars involves a gap vastly larger than the entire planetary region we normally think of as our solar system. The inner pair has a much tighter arrangement. Alpha Centauri A and B orbit one another roughly once every 80 years. Their separation changes as they move along an elliptical path, ranging from distances comparable to the orbit of Saturn to distances somewhat beyond Neptune's average orbit. That makes A and B a relatively compact stellar pair when compared with Proxima. The whole system, therefore, has a layered structure. 2 large stars move together in the center, while the much smaller red dwarf follows an extraordinarily wide orbit around them. That arrangement matters for spacecraft design. A probe built for a high-speed encounter with Proxima would approach the nearest part of the system at tens of thousands of kilometers per second. Its trajectory would be chosen years in advance to pass near specific targets, perhaps Proxima itself or Proxima b. Continuing afterward toward Alpha Centauri A would require crossing another enormous region of space. At 20% of light speed, a distance of 0.21 light-years could theoretically be crossed in a little over 1 year, if the geometry were favorable and the spacecraft already happened to be moving in the right direction. A real mission would face much more complicated geometry. Proxima, Alpha Centauri A, Alpha Centauri B, and any planets around them are all moving. A probe, optimized for one encounter, may be heading in a direction that carries it far from the others. Changing course at such high speed would require additional propulsion capability. Slowing down enough to conduct extended observations would be harder still. A Starshot-style spacecraft gains its advantage by remaining extremely small and fast, so it would have little ability to perform a leisurely tour of several widely separated stars. Even communication within the system has meaningful delay. A signal sent from Proxima toward Alpha Centauri A and B could spend months traveling between them. A future settlement near one member of the system could therefore experience delays even when communicating with neighbors orbiting the same gravitational family. The phrase Alpha Centauri can make the destination sound compact, almost like reaching one point on a map. In physical space, it resembles a vast collection of separated regions. Reaching Proxima means reaching the nearest star. Reaching the entire Alpha Centauri system would require navigating distances that remain enormous even after the 40 trillion kilometer crossing from Earth has already been completed. And the central pair has become especially interesting for another reason. Recent observations have produced evidence that one of those nearby sun-like stars may itself host a giant planet. Crossing Alpha Centauri remains far beyond anything our spacecraft can currently do, but studying the system does not require waiting for an interstellar mission. Modern telescopes can extract information from light that has already crossed the gap for us. One of the most difficult goals is direct imaging, where astronomers attempt to detect light coming from a planet itself rather than discovering the planet indirectly through its effect on a star. Alpha Centauri A makes this especially challenging because it is one of the brightest stars in Earth's night sky. Any planet nearby would appear extraordinarily faint beside it. The James Webb Space Telescope approached the problem using its mid-infrared instrument, usually called MIRI. Infrared light has wavelengths longer than visible light, and warm planets can emit strongly at some of these wavelengths. Webb also used a coronagraph. A coronagraph places a carefully designed mask over the bright image of a star, suppressing much of its glare so astronomers can search the surrounding region for much fainter objects. During observations in August 2024, Webb blocked Alpha Centauri A and found a faint source nearby. After researchers accounted for light from Alpha Centauri B and other possible sources of interference, the object remained visible at a position consistent with a possible planet. The source was more than 10,000 times fainter than Alpha Centauri A. Analysis and computer modeling suggested that it could be a gas giant with a mass roughly comparable to Saturn. Its possible orbit is also surprisingly familiar in scale. The candidate appears consistent with a planet traveling around Alpha Centauri A at roughly twice the distance between Earth and our star. That would place it at around 2 astronomical units, within a region comparable in size to the inner part of our own planetary system. The detection remains a candidate. Astronomers have to eliminate several alternatives before a planet can be considered confirmed. A faint point of infrared light might come from a distant background object, an unrelated body passing through the field of view, or an effect produced by the telescope and its instruments. Repeated observations are especially valuable because a real planet should move in a predictable way around its star. NASA material, updated in 2026, continues to describe the Webb result as evidence for a potential planet around Alpha Centauri A, rather than a confirmed world. That uncertainty is part of the reason the observation is so interesting. If the object is confirmed, it would give astronomers an unusually close opportunity to study a giant planet orbiting a star broadly similar to our own. At approximately 4.37 light-years away, Alpha Centauri A is vastly closer than most planetary systems studied by Webb. Direct imaging can eventually reveal information that other detection methods struggle to provide. Infrared measurements can constrain a planet's temperature and brightness. Repeated observations can help determine its orbit. With favorable instruments and targets, astronomers can sometimes begin separating information about an atmosphere from the light of the planet itself. Even Webb remains more than 40 trillion kilometers from Alpha Centauri. A spacecraft inside the system could observe from completely different distances. Instead of trying to separate a planet from the glare of its star across 4 light-years, cameras could approach the planet closely enough to resolve far more detail and measure its surroundings directly. The contrast is remarkable. Our machines remain confined to the neighborhood of our own star, while telescopes are already beginning to identify possible destinations around the nearest sun-like stars. By the time the first interstellar probe is ready to launch, Alpha Centauri may contain a much richer catalogue of known worlds than we have today. The first spacecraft reaching them, however, would probably have very little time to look. At 60,000 kilometers per second, decades of preparation would lead to an encounter measured in hours. The most realistic first interstellar mission may therefore look less like a single historic spacecraft and more like a swarm. Breakthrough Starshot has proposed sending large numbers of tiny probes toward Alpha Centauri rather than depending on one vehicle to survive every stage of the mission. Individual nanocraft could be lost during acceleration, damaged by interstellar dust, or fail electronically during the decades-long crossing, while others continue toward the system. That redundancy matters when replacement is impossible. Once the probes are several light-years from Earth, engineers cannot repair them or respond quickly to unexpected events. Each surviving spacecraft would have to manage its own navigation, power, communications, and scientific instruments. The final approach would be especially demanding. Long before reaching Alpha Centauri, onboard cameras could begin comparing the observed positions of stars with stored navigation maps. As Proxima and any planetary targets became brighter, the spacecraft could refine its trajectory and determine exactly when to begin its most valuable observations. Earth would have almost no role in those final moments. A command transmitted from mission control would need more than 4 years to reach a probe near Proxima. By the time controllers learned that the spacecraft had entered the system, the encounter itself would already have happened years earlier. Everything would depend on instructions written before arrival and decisions made by the probe's onboard computer. At approximately 20% of light speed, the encounter would unfold extremely quickly. The spacecraft would travel about 60,000 kilometers every second. 1 astronomical unit, roughly the average distance between Earth and our star, would pass in about 42 minutes. A probe approaching Proxima b could therefore move from millions of kilometers away to closest approach and back into deep space during a very short observing window. Its cameras might attempt to photograph the planet at changing angles as it passed. Other instruments could measure charged particles, magnetic conditions, dust, and the surrounding interstellar material. Observations of Proxima itself could examine its radiation environment from a location impossible to reproduce with telescopes near Earth. The mission would have to collect those measurements automatically, while storing enough information to transmit afterward. Timing would be critical. A camera that begins imaging too early may see little more than a faint point. Waiting too long could mean passing the best viewing geometry before the instrument reacts. The target might occupy its most useful position for minutes, while the spacecraft covers tens of millions of kilometers. After closest approach, there would be no turn back. A Starshot-style probe would continue outward because it lacks the propulsion system required to erase its enormous velocity. Alpha Centauri would begin shrinking behind it, while the spacecraft prepared for a completely different challenge. The data would still be trapped more than 4 light-years from Earth. Any photographs or measurements successfully transmitted would travel at light speed, requiring another 4 years or more to reach receivers here. So, a mission launched toward Alpha Centauri could spend a little over 20 years crossing the interstellar gap, experience its most important scientific encounter during a period measured in hours, and then make Earth wait several additional years to discover what happened. That strange timetable may define humanity's first visit to another stellar system. Decades of engineering could culminate in a machine racing past another world too quickly to stay, carrying observations that nobody on Earth can see until years after the encounter is already over. Only then does the phrase, 4 light-years, reveal everything it has been hiding. Proxima Centauri remains about 4.25 light-years from Earth. Written in kilometers, that is roughly 40.2 trillion. Measured with the astronomical unit that works so well inside our solar system, the distance becomes about 268,000 astronomical units. Those numbers have not changed during the journey through this video. What has changed is what they now contain. 4.25 light-years represents far more than a large amount of empty space. Crossing it quickly means giving a spacecraft enormous velocity, and enormous velocity demands energy. The same speed makes microscopic gas and dust increasingly dangerous. Reaching the destination while still moving at tens of thousands of kilometers per second creates a braking problem almost as important as the original acceleration. Communication remains tied directly to the distance itself. A spacecraft could someday cross the gap faster than anything humanity can build today. A radio message still cannot make the journey in less than about 4.25 years. That difference separates several very different meanings of interstellar travel. A spacecraft moving like Voyager 1 belongs to a timescale of roughly 75,000 years. Civilizations could rise and disappear during a voyage like that. Even the record velocity reached by Parker's solar probe, if it could somehow be maintained directly toward Proxima, would leave the crossing at roughly 6,600 years. A proposed nanocraft moving at 20% of light speed finally changes the unit from millennia to decades. The reduction comes from pushing the spacecraft toward an extraordinary speed while shrinking its payload to only a few grams. That combination may eventually allow a machine launched within one human lifetime to reach another stellar system during the same lifetime. People are a very different payload. Habitats, shielding, life support, stored materials, repair systems, and every kilogram of structure would increase the energy required to reach the same velocity. The first photograph taken from inside another stellar system could therefore arrive generations before the first human traveler does. If people eventually settle around nearby stars, distance may shape those communities in ways that have no close equivalent on Earth. Travel between neighboring systems could remain difficult even for a technologically advanced civilization. News would cross the gap only as fast as light. A message sent from Alpha Centauri would describe something that happened more than 4 years before anyone on Earth received it. an answer would begin another journey of the same length. Two communities could therefore remain connected while experiencing events years apart. That may be one of the strangest consequences hidden inside the word nearest. On the scale of the Milky Way, Alpha Centauri really is extremely close. Our galaxy stretches roughly 100,000 light-years from side to side. A separation of 4.25 light-years is almost negligible on that map. Human experience uses a very different scale. Our fastest long-lived interstellar spacecraft moves only a tiny fraction of the speed needed to make the crossing convenient. Concepts that could reduce the journey to decades require engineering far beyond anything currently operating. Even after arrival, Alpha Centauri spreads across an internal distance large enough for light to spend months traveling between Proxima and the central pair. The nearest stellar system was never chosen because it offered an especially dramatic challenge. It is simply the closest one available. Tonight, Proxima Centauri remains an invisible red dwarf from most ordinary human viewpoints, too faint to see without a telescope, even though no other known star beyond our own lies closer. Photons reaching Earth from Proxima tonight began their journey more than 4 years ago. They crossed roughly 40 trillion kilometers without stopping, carrying the image of a star as it existed years in the past. And even for light itself, that was the shortest possible journey from another star to us.